Okay, hi. I'm recording a brand new lecture for you today. Our last kind of topic of the semester for this class about the Big Bang, Einstein, and relativity. And just a warning, a content warning here. Prepare to have your mind absolutely blown away. It's okay if you don't understand everything the first time. That's why I'm here to answer your questions to help us get through this together. But this is really cool stuff. Also, keep in mind that I myself never took a relativity class when I was in grad school. And so my knowledge of this is is I learned it through and from Catherine Schaefer, who helped design this course with us and is a physicist at SAIC. Brilliant and accomplished and really good at explaining things. So the point of this, as has been the point of all of the lectures in this class, is not necessarily that I'm going to teach you everything about relativity and you're going to be an expert. It's more to talk about relativity and the Big Bang and Einstein in the context of, what is science, how is science done, what are the controversies of science, etc. So let's start. So let's start with the Big Bang Theory in two parts. So will be two lectures. This is the first lecture for this week's class. We'll talk about gravity and equations and sort of how physical theory functions, and then we'll talk about Einstein as the iconic genius outsider, and then we'll talk about relativity, like what it is and what it is not, and I will probably go over this in more detail when we meet on the Zoom. And then we'll talk about arrogance in a good way, and you'll see what I mean by that. And then next week, we'll talk about arrogance in a bad way, and the Big Bang Theory formally, and the idea of an expanding universe, etc. Some bonus themes are math is weird and aesthetics are actually more important than you might think. Before we do that, we are going to do this group exercise in class tomorrow, so keep this kind of in mind. What I want you to do is in groups or maybe on your own, collectively remember a core rule from geometry, for example, about triangles or distances between 2 points or parallel lines. Consider where this rule came from. Did we make it up? Is it a fact of nature? Does it apply here on Earth or does it work everywhere in the universe? And then finally, I want you to break the rule that you remembered, that you came up with. Think of a shape or a scenario or a possibility where the rule doesn't hold and is violated. And tomorrow, or when we meet together on the Zoom, we will write our rules on the board and then describe what's going on. Let's start then by what we mean by a theory. What does a theory look like? What is a theory? Can it be proven? Again, we've talked about a lot of this with respect to, Popper and falsifiability, right? So this shouldn't be new. Where do new theories come from? And if there are multiple theories that describe one phenomenon, how do we decide between them? And if a theory is wrong, do we throw it out completely? Do we, how do we deal with that? So that's something we'll talk about. So let's start with a real physical theory. This is the theory involving two objects with a mass, right? So you have mass 1 and mass 2, and we can describe the force between them using their masses r, the distance between the two objects, and g, which is a constant that stands in for gravity. So this is a kind of an equation relating force to gravity. Okay, this is something that we learn in Physics 101 in most universities. This is Newton's law, right? Get me out of the way here. Newton's law of gravity, basically describing how the force between two objects is proportional to their multiplication of their masses divided by the radius squared times gravity. Um, so some things I want you to keep in mind are, what is the model of gravity here? How does this theory function in the real world on Earth? And what would it mean for this theory to be right or for this theory to be wrong? So if we just use math, right? We're just using math here. We can use the Newtonian gravity descriptor to derive a relationship between two things in the real world. So this is a law which Newton described, right? Which we can then use to describe the relationship, for example, between the orbital period of a planet and its distance from a star and the mass of that star. Okay, and so if you work through the whole math, we derive the orbital period at the end here as being equal to a couple constants, right? 4 pi squared r cubed, which is the distance of that planet from the star, let's say the sun, divided by gravity, Newton's law of gravity, right? Oops. Times the mass of the star, not the planet, the star. And this works pretty well. We can use it to describe the orbital paths of all the planets in our solar system. So therefore, Newton's law of gravity is true and real, right? Not exactly. So what does it mean then if this what does it mean if this model gives predictions for orbits that match what we measure? What does it mean if this model is, for all intents and purposes, correct for the planets in our solar system? What does that mean? Especially because this model is actually, I'm telling you right now, not true for everything in the universe. What does it mean then if it's not true? And what doesn't it mean if this model works for all the planets in our solar system? Okay, what does that mean? And what doesn't it mean? Okay, hold on. Okay. So the right, oops. Oh my gosh. So the fact that the model is right for this particular instance, for example, Earth or for our solar system, that doesn't necessarily mean that the model is right everywhere. Or more accurately, it doesn't mean that the model is complete. It also doesn't mean that future measurements with greater precision will necessarily continue to perfectly agree with this model. So let's go through a little bit of a history of our understanding of physics then, and then I'll come back to this model of gravity from Newton. So in 1632, Galileo essentially begins, is like the sort of what we might consider the first classical physicist. Galileo is thinking of ships literally passing each other in the night, and arrives at this idea that there is no absolute meaning of stillness, and there's no absolute definition of motion. So to you, I'm motionless in this chair, or I'm sitting, I'm not moving in space. Although my hands are moving in space, my body is just generally not moving in space. Galileo said that doesn't mean that I'm not moving, and it also means that there's no way to define something as being still. Okay? This is the beginning of our very basic understanding of relativity, and I'll get to that in a second. About 50 years later, Newton derives the laws of motion, okay, and universal gravitation. and is arguing that the formulation of motion per Newton depends on an absolute meaning of time and usually assumes absolute space. So the apple falling, those trajectories that you have to draw in physics, all of that is Newton. And that is what we might think of as non-relativistic, macroscopic, non-quantum classical physics, meaning that those laws of physics hold for the things that Newton was observing on our Earth. And they actually, as we saw in the previous slide, hold for our whole solar system as well, within a reasonable margin of potential error. Now, fast forward 200 years, okay, Maxwell works out the mathematical laws of electricity and magnetism, which seemed to imply a constant speed of light, regardless of the reference frame. So this is weird, right? If light is moving through all space and through all time, as we'll learn in a second, at a constant speed, this calls into question the ideas that Newton codified as laws 200 years earlier. And just 20 years after Maxwell, the Michelson-Morley experiment showed that light does not require a medium to travel through, meaning there's no ether of space. Light is not traveling through anything. Light is just moving. And we'll get to that in a second. And then just 20 years after that, Einstein essentially figured it all out. It took him about 10 years. He started with the theory of special relativity, and then we moved to the theory of general relativity. And what Einstein did is he said Newton is wrong, or Newton's laws are not complete. They're not right in all circumstances. And he therefore removed this idea of absolute space and time, and in the process of this, made a new theory of gravity that kind of contradicted the theory of gravity that Newton was writing about 320 years earlier. So let's talk about relativity. And I'll ask this question when we meet in person, but what do these vocab words mean to you, right? So we have relativity, Galilean relativity, special relativity, and general relativity. I think we all know what relativity means, but we'll define these terms and talk about these terms when we meet on Zoom. In particular, I want you to think about how they relate to subjective experience and whether they relate to anything that we experience normally, that we can perceive with our senses, right? That our eyes and our ears and our brains can perceive of in real time on a human scale. And so there are a lot of answers for this, but I'll explain more when we kind of talk about it in person. So there are kind of two ways to think about relativity. There's kind of everywhere relativity, right, which is variations in subjective experience and judgment based on different social and cultural, personal frames of reference. Like this today is cold, relatively cold, for me, for April. Okay, that's kind of the sort of relativity of our subjective everyday experience. Relativity in physics is not subjective. Relativity in physics is objective. It's an objectively measured feature of space, time, and motion, which deals with space-time frames of reference. And if any of you have seen Christopher Nolan's new film called Tenet, he deals with this idea of objective relativity as it pertains to time. It's really interesting, and I think we'll talk about that a little bit. Excuse me. In this bubble of physics relativity, we have Galilean relativity, which is everyday perspective-based differences in assessing motion, meaning if I am in a car driving on the freeway and I'm going 80 miles an hour, I'm going to appear to be moving faster, and I will literally pass by a car that is moving at 60 miles an hour. And that car will actually appear, if I consider myself to be stationary in my 80-mile-per-hour moving car, that other car will appear to be moving backwards. That's Galilean relativity. Even though to an observer on the side of the freeway, we're both moving in the same direction. To me, if I'm moving 80 and I'm passing a car that's moving 60, right? I'm going like this car's going like this, a little bit slower. If I'm going this fast and this car's going this fast, to me, if I'm staying still, this car will appear to be moving backwards. That's Galilean relativity. Special relativity is what Einstein started arguing in the early 1900s and is basically defining differences in the structure of space and time themselves due to relative motion. You're already confused, and that's okay. And then general relativity is just special relativity, but dealing with the curvature of space-time and applying to the entire universe and its relationship to gravity. Galilean relativity and subjective relativity describe features of everyday experience, but have very little, if nothing at all, relatively little, to do with Einstein's theories, and I'll explain that more in a second. These two things, special relativity and general relativity, are together Einstein's theory of relativity, which, remarkably, 110 years later, is still the reigning theory of space and time and gravity, and it's how we kind of define and talk about and think about our entire universe. So if you're interested in the overlap between these two things, which Catherine, who made this slideshow, argues exists, this would be a plug for taking her course, Articulating Time and Space. All right, so let's talk about Einstein's early career, and then we'll talk about what relativity actually is. So in 1902, Einstein is young, and he takes a job at a Swiss patent office after completing a degree in undergraduate physics. In 1905, as a worker at the Swiss Patent Office, Einstein publishes two papers that would totally revolutionize physics. One is on quantum physics, and the other is on special relativity, which is what we're about to talk about, as an outsider. Meaning he was not in grad school, he doesn't have a PhD or any of that, and he publishes these two papers. And in 1907, 2 years later, he starts to work on general relativity. So he takes his ideas of special relativity and then applies them to the whole universe, the curvature of the whole universe, and specifically gravity. And then in 1909, he's offered a professorship, which let him work as a physicist full-time, so without a graduate degree. In 1916, he finally completes his theory of general relativity, which took 8 years of math. And then in 1917, he takes this amazingly arrogant but a very important leap, applying his theory to the entire universe and launching the field of scientific cosmology. So this is the good arrogance that we're talking about, the good scientific arrogance. He takes a leap of faith and is amazingly arrogant, says, I've solved the math of the universe, basically, which is pretty remarkable. So let's talk about what it means to be a genius or an outsider or a crackpot in science, right? Sorry, I thought I had text here, but I think that actually this is saved for us to have a discussion in class. I think I removed it, actually. So we'll have a discussion on this in class on what it means to be like sort of a genius or an outsider or a crackpot from a scientific, vantage. So what is relativity, right? Why are we talking about this? What's the big deal? Why was Einstein so revolutionary? So let's start with Galilean relativity. It's pre-Einstein, but it did influence his ideas. So basically, Galileo says it's not possible to distinguish between being at rest and between smooth motion in a straight line. There's no test that you could perform to tell if you were really moving or if you were actually at rest. And here are some excerpts from a book published in 1953. Translated, in 1953, published by Galileo, talking about this phenomena. And it's basically what I just said, right? Well, he was talking about it with ships. There was no cars in the 1600s, but if you're a ship that's going faster than a ship that's next to you, that ship that's next to you will appear to be moving backwards. There's no way to define who is still and who is in motion, right? You can determine this based on wherever you are, or whatever your fixed vantage point is. So there's no universal definition of in motion, and there's no universal definition of stillness. And here's a great example. If I am climbing to the top of my sailboat, and I have a pair of binoculars, and my sailboat is moving this way, to me, if I drop my binoculars, they will appear to fall straight down onto the boat. That's because I am fixed on this boat and we're both moving this way. The binoculars are also moving this way. But to someone standing on the shore, the binoculars will appear to follow this path. As the boat is moving and the binoculars are dropping, to someone watching from the shore, they're going to appear to move forward with the boat, right? If we're just watching the binoculars. Of course, we'll all be moving forward as well, so we'll end up over here by the time they hit the bottom of on the bottom of the boat. There's another video here which I will show in class tomorrow. So in everyday experience, for the most part, we act like we have an absolute frame of reference, which is the Earth, right? And this is where Newton is coming from. So thus we intuitively respond that a person in a train is really moving and a person asleep on the platform is actually at rest. Classical physics undid some of this. So Newton and others said that uniform straight motion is equivalent to rest, and they are indiscernible by any experiment, experience, or measurement. You can't actually determine if someone is quote unquote at rest. Oops. Oh my gosh. Not only does place or moving or stillness have no absolute meaning, but there are really these are really non-concepts. They actually just don't exist in the world, right? We haven't even gone to modern relativity yet. This is just pre-Einstein Newtonian relativity, where you have no actual physical mathematical explanation for moving versus still versus at rest versus in place versus whatever. Unless you assume that the Earth is an absolute frame of reference, which you absolutely can do, and then you can derive a bunch of equations to describe that. So then let's jump ahead to special relativity. Special relativity says that speeds of motion, which are always relative to the observer, okay, this is similar to Galilean relativity, except for the speed of light, which is the same relative to all observers. So the ship is moving relative to me, and if I'm on a ship that's also moving, that ship is going to be moving at a relatively different speed to me. However, if that person on the ship is shining a flashlight, that light to me and to another ship that's moving and to someone on a distant planet, that light is going to be moving at the exact same speed relative to all of us, to all observers, all physical observers. To make this work mathematically, space and time must be derived as a four-dimensional space-time. Meaning, in order for this to work out mathematically, in order for Maxwell's observation of the speed of light being constant to work out mathematically, space and time must change. There are no absolute spaces and there are no absolute times. They must stretch and contract in response to relative motion. Meaning, the faster I'm moving, the slower time is progressing. I froze. This happens a lot. So, and I was right at the good part too. I was right at the meat of the story here, but oops. So, of course, I'm always at the punchline, and then there's some technical difficulty. I don't know why QuickTime always does this. I can't wait to stop recording these videos. Anyway, so the punchline here, right, is that because the speed of light is constant, and this is an observation that was made at the late 1800s, right, before sort of Einstein derived this theory of relativity, special relativity. The conclusion is, if the mathematical equations are going to work out, then all of Newton's stuff doesn't really work. It doesn't really apply because he's assuming there's like this absolute space and this absolute time, and there is not. In fact, space and time are not absolute things. They are actually a four-dimensional space. They're linked together, and their fundamental properties, in order to describe time, for example, it's dependent on the observer. And the observer doesn't have to be a person. It can just be like an observer in the universe, an object or whatever, an atom, an observer's perspective. So where I am, how massive I am, and how fast I'm moving, and in what direction and all of that, right? So the reason you're confused is because this is a truly lovely and elegant idea, but the math is really complicated. And so I actually have several videos and several equations and stuff that we'll go over tomorrow in person. It's just easier than trying to say it on the Zoom, which will help it solidify this idea of space and time as stretching and contracting in order to make room for relative motion, right? But the reason really that this is a lovely and beautiful and elegant idea is because it's actually true. It's something that we can observe all the time. Unlike Newton's laws, which are only observable at smaller, relatively smaller spatial scales, like Earth or our solar system. So moving from special relativity to general relativity, okay, introduces just the concept of gravity. That space-time is not only responding to motion, right? It's not only responding to an object's motion perspective, but it's also responding to an object's matter, how big it is, how large it is, how massive it is. So, and this can be any form of energy, but matter is just one of these, the easiest to kind of grasp, okay? So space and time are stretching and contracting based on how fast something is moving and also how massive it is, meaning the Earth is a very massive object, right? And can actually curve space and time as a four-dimensional thing, right? As a four-dimensional variable. And so therefore, curvy or curved space-time is gravity. Gravity is not a thing. It's not a number. It's not an entity that we can describe universally. It's just the existence of curvy space-time. So, this is actually a new theory of gravity over what Newton was saying um, a long time ago, right? So that theory that we started with, um, it's not true, or it's not complete, because we have now a new theory of gravity as introduced by Einstein, which describes uh, how gravity is actually kind of a manifestation of curvy spacetime. There's a new equation which describes how it works. So this is a highly misleading picture, but I think it's a really good picture to kind of think about what could be happening here, and then also to open up a conversation that we can have about how we can use aesthetic renderings to describe very complicated physics questions. So here we have the Earth and the Sun, both really massive objects which are bending and curving space-time, which is represented by this two-dimensional space-time grid almost, right? So as the Earth bends space-time and the Sun bends space-time, you can see the Earth bends space-time just enough to stay in its orbit, but the Sun bends space-time more to keep the Earth in orbit around the Sun. That's what's being depicted in this image. So I want to talk about why this image might be good and why this image might be problematic. But before we do that, we're going to have to talk about, we're going to have to really clear up like what space-time actually is. And so I've got a few videos to show you tomorrow when we meet on Zoom. But we've got a new equation now for gravity, and I'm not going to explain this because there's a lot going on here, but essentially general relativity and Einstein derived an entirely new equation to describe gravity, G here, that is totally different than Newton's theory of gravity, right? So remember, Newton's law of gravity worked when we calculated the orbit. So what does that mean? Does that mean that it's true or not? Because if it worked, then why am I saying it's not true, right? But what doesn't it mean? So Newton's law of gravity is not necessarily wrong, but it's not right. And that's because it's not complete. And that's because it really only applies to things at smaller, relatively smaller scale. So, for example, our solar system is a relatively smaller scale, and so Newton's law of gravity will work in our solar system. It won't be exactly perfectly precise, but it will be precise enough for us to not care, right? Especially on Earth. But if we use Einstein's updated definition of gravity, we actually learn that Mercury's orbit, right, doesn't actually look like this perfect oval that's static around the sun. It actually moves in very complicated ways that we can now understand with more complexity using Einstein's theory of general relativity. So consequently, with this updated theory of gravity, right, we can make some very new interesting predictions and applications. And geometry really isn't the same everywhere, like Newton was assuming, right? And so we can't just apply Newton's theory to the whole universe, but we can apply Einstein's theory to the whole universe. Because the ways in which geometry is not the same everywhere, we can model now through math. So we can actually say that math itself can change according to the situation that you're considering it. And this brings us back to the activity that we're going to do at the beginning of this lecture. And so as we move into thinking about relativity, general relativity, and how we depict that, right? I mentioned that these images can be quite problematic, but I want to talk about why. I want to talk in class, right? Why these images are problematic, what's going on, what works, what doesn't work, and why. So we have the sun, a neutron star, and a black hole, which are increasingly more massive and increasingly curving space-time around them, to the point where a black hole curves space-time so much that lots of things happen. Which, if you've seen the movie Interstellar, does a really good job of addressing, actually. So I'm not going to talk about black holes in this particular lecture, but I am going to mention that black holes themselves are a very complicated curvature of space-time that cannot be described by Newton's equations, by Newton's laws. We can only use Einstein's theory of relativity, of general relativity, to understand what black holes are and how they operate. So bookmark this and ask me about black holes tomorrow in class. Also, Catherine put this photo in here because one of her students got this equation tattooed on their arm, and this equation is actually the equation of the universe, which is Einstein's most arrogant leap, and how I will conclude this lecture before we get into the second lecture, right? Which is that he took his ideas of general relativity and treated the entire universe as a physical system, and how we can use one single equation to describe and apply to that entire system, and what happens when we do that scientifically. So I want you to think about that. So we definitely have a lot to go over in terms of like what is relativity. I hope I've given you kind of an intro to it. It's very difficult for me to lecture to a computer about what relativity is without not also getting your questions about it. So I've got videos lined up. I've got demonstrations lined up. So make sure you come to the Zoom so that we can understand what relativity is before we move into next week when we talk about the Big Bang and our expanding universe. All right. So I will see you then next week.